Hi everyone, and welcome to this practical slash lecture that we will do today instead of a in-person session. We will look at linear regression and logistic regression in R. We would like to understand how to estimate the models, how to interpret the models, and how to do some visuals with that. And let's jump right into it with linear regression. I have selected a nice dataset where we can run a cool linear regression. If you want to do that at home as well, it is the student performance dataset, which has some data on students, and as outcome variables, we have their performances or their results or grades in classes. You can follow this link or just Google it and then look at this data set. And here, for example, we have the outcome variables. This one is our variable of interest. It's called G3, and it is the final grade of the students from 0 to 20. And there are a lot of variables that we can throw into a linear regression model to try to understand what shapes the final grade of a student and what maybe doesn't. Let's get cracking by loading the data in our R environment. I have downloaded the data as a CSV file, and it is in the same folder, so I don't as this file, so I don't need any path. And for me, the file is called studentmet.csv. Let's set the option header as true. It means that the first row is the headers of the variables, or the names of the variables. And here we have the separator semicolon. You could also use the read CSV2 function. It automatically understands that the separator is semicolon, but we just do it like this. It doesn't really matter. Then we have this data. We load it and we get all these nice variables. And we would like to understand, let's write that down. We would like to understand the impact of a set of independent variables on a dependent variable final grade. And the independent variables that I selected are the student's age, the student's mother's education, father's education, the study time, so how much you actually studied, whether it helps or doesn't help for the grade, the number of previous failures, and the gender. And all variables, I looked at it already, are in a good shape, except for the gender variable. It's it currently, let's take a look at it. Data sex. We have F's and M's. We don't want that. We would like to have it as a 0-1 variable. We definitely need that. And for that, we can just go into our data set, pipe, and create a new variable. We just call it female. And we use the if-else function. If the current sex variable has the value f, then we want it to be 1, else we want it to be 0. Okay, of course, I forgot to load the tidyverse. Then R doesn't know our pipe operator. Let me zoom in. I don't know if you can all read it, but now we have our new column. Now we have 34 instead of 33, and now we fit our model. Really easy. We call it model. We assign a linear model with the independent variable G3, so the final grade, and then we just use our variables age plus mother's education plus father's education plus the study time plus the number of previous failures in these exams plus the newly created female variable. And we specify our data. Our data is our data set called data. Pretty easy. Let's run this. and we see it works. We get our model here as an object, a list of 12 objects, and we now have estimated our model. Now we want to inspect it. Let's do this in a really basic way. We can look at our model coefficients by just typing the model name. Then with the $ operator, we can move to one of these 12 things or vectors that are specified here. So if we want to have a look at the coefficients, we just use model $ coefficients, and we get our regression coefficients. All right, we see some negative coefficients, some positive coefficients, intercept, and so on. But it's currently not really enough to make a good interpretation of these coefficients. So let's use the summary function. And here we get a little bit nicer plot. We see again which model we ran. We can see again our intercept. We can see these are the regression coefficients. So for example, study time has a regression coefficient of 0.4. We see the significance of each of the regression coefficients. So here you can see the codes. If something has 2 stars, it is significant on the 0.1% level. If something has a point like this, it's significant on the 0.5% level, and so on and so forth. And then we have, which is important, our statistic called R-squared. The higher this is, the better our model is in general. So here we have 16.8% of the total variance is explained in the outcome variable, is explained by our model. So actually it's not that good. R-squared can be between 0 and 1, and we would strive it to be like higher than, as high as possible. So 0.16. In general, we don't have a really good model here to explain the performance of the students, our outcome variable G3. But we can do these summaries, which are really important, even a bit nicer using the package Stargazer. Let's load this package. Maybe you need to install it if you haven't. And then the function is called the same as the package Stargazer. You specify the model. Then you give it a type. It can be a LaTeX, HTML, or text, but we want text because we want to see it directly in our R file here. Then we would like to see the confidence intervals, so we set CI to true. Our confidence interval level should be 0.95 because we want to see the confidence boundaries for a 95% confidence interval. We set the single row option to true, so everything should be in a single row, that it's less messy. We want again stars, significant stars, and we set the cutoffs 0.05, 0.01, so these are the typical cutoffs on 0.001. And then we don't want a header. These are all like optional specifications, but let's do it for now. And we can even set a title, so we can make really nice plots here, or summary tables. We just call it linear regression model, quite easy. And then we get this output, even a bit more beautiful table. Again, these are our regression coefficients. We have the lower and the upper boundary of the confidence interval. We have the significant stars. So for example, we can see the mother's education does have a significant positive effect on the outcome variable. The father's education, for example, does not have a significant effect. And we have highly significant variables in the number of previous failures and the gender. Again, we have our R-squared. Of course, it doesn't change. It just looks a little bit nicer. And here again, we can see our significance levels. All right, so this is the Stargazer package used to produce a little bit nicer regression outputs. Now Now let's interpret these coefficients, and I have picked two because it's I would like to interpret with you the sex variable and the study time. And in general, the interpretation statements with respect to linear regression models are like these. We see that this is a significant effect of minus 1.179. So if you are a female, let's write it down. Female students had on average, and all other variables held constant. So this is really important. We always need with the statement on average and all other variables held constant. This can also be written as C.P, which means ceteris paribus. It's Latin, but you can just abbreviate with CP. So you can always write on average CP, and then you have the correct interpretation. So female students on average and all other variables held constant showed a lower grade of how do we write that? Show a lower grade of minus 1.179 compared to male students. This effect is significant on the, and now we see we have 2 stars, so it's significant on the 1% level. 1% level. All right. So what is important? We need to state the significance. We need to state the on average and ceteris paribus, and then we need can state our effect or our coefficient. And now for study time, let's look at study time. It's just the hours studied, and we have an positive effect of 0.4. So we can say each additional hour of studying increased the final grade on average CP by 0.5 points. However, this is important, this effect is non-significant, or this coefficient. Let's write coefficient here as well. We need to be careful with the term effect. So here this is quite easier to interpret. We just increase the study time by 1 hour, and it would, if we would have a significant effect, increase the grade by 0.4 on average CP. But this is a non-significant effect, so we can't really make sense of it, can't really logically interpret it. But this is just an example to show you how to interpret the regression coefficients. Now that we have done that, let's look at the 2 plots that we also looked at in the lecture videos, the coefficient plot and the residual plot. And we can start with the coefficient plot, where we need again the package coef_plot. There are other options, but I like this package, so let's do it with this package. And again, we have a really easy, the function is just called coef_plot as well. We specify the model, and now we have a lot of arguments to specify if we want that or not, but I will do it for now. So we first give it our model, then we don't want to see the intercept. Actually, we are not that interested in that, so we set that to false. But we want to see the error bars, so we set that to true. Now let's for now run this. Do we already get an output? Yes. So we get a quite nice coefficient plot really quickly. We could give it some titles, so I don't know, we could label the x-axis by coefficient estimate, and we could label the y-axis with the independent variables. I don't know why it currently doesn't show these new labels, but it's not that important. Let's see if it changes. Nope. Okay, I don't know why, but it's not that important. Let's zoom out a little bit. So here again, we just see our regression coefficients from this table. For example, look at female, it's minus 1.179, and this is minus 1.179 here again. And we just have this in a visual manner and not only in a table. And we can also immediately see the significance of these coefficients, because every coefficient that overlaps with zeros here, is non-significant. It's not significantly different from 0. We cannot say certain enough that this effect is, or this coefficient is not 0 or different from 0. And we can see that female, the number of previous failures, and the mother's education are significant because they don't overlap with 0. We could, in principle, specify a lot more stuff here in this plot, but I think it's already a really easy and efficient tool to get this coefficient plot. It's also easy to see the negative coefficients on the left and positive coefficients on the right. And also for the residual plot, it is even easier to plot this. You can just use the plot function. You give it your model, and then there's an argument called which, and there you have different plot options, and we just select the first one, and it will give you the residual plot. And it's called residuals versus fitted because it compares our fitted values, so values predicted by our model, compared to their respective residuals. So residual is just the difference between the fitted value, so predicted value, and the naturally observed, or the value in the data. So for example, let's look at this observation. We predicted our model would suggest a grade of around 4 points for this student. Let's say this is a student. But we were actually around 4 points off, so the -4. So this is our residual. And in principle, what we want to see here is actually nothing. There can be variation, but it should be random. As I stated in the lecture video, we should not observe a pattern in our residuals here, because then it might be that we are missing out on an important variable, or our variables cannot pick up all the patterns in our data. So here, this red line should at best be as straight as possible, around 0. And here, well, we have some slight pattern that we would have our residuals go downwards a little bit, but I think it's not as problematic in order to prevent us from running this linear regression. I think we are still fine, but this residual plot is really important to just check on the assumptions for linear regression. All right, so now in this video we learned how to plot a residual plot and coefficient plot. We learned how to print out a nice regression table, how to run the regression model, and very important, if you didn't do that in a stats class or anywhere before, how to interpret the coefficients. Next video will continue with logistic regression.